To conclude our discussions about NS equations, I'll just tell you one more interesting thing, which is how we can transform the NS equation into a non-dimensional form. By non-dimensional form, I mean I will substitute every variable, well, nearly every variable here with its non-dimensional counterpart. And then our equation will be just an equation about non-dimensional variables. So we'll define a non-dimensional velocity, a non-dimensional time, etc. So the equation we get there is what we call the non-dimensional NS equation. So how can we do that? We need to neutralize all the dimensions of the variables, right? So we can do that by the process of scaling or dimensional analysis. First, we need to introduce some characteristic properties or characteristic quantities of the system. So let's define L to be the characteristic length of the system. By this, I mean that we assume the length scale of our fluid system, of our problem is of the order of magnitude of L, okay? And omega is the characteristic frequency of the system. The frequency has a dimension of what? 1 over time, right? So we introduce the omega obviously to neutralize the dimension of which variable? Of t. The t here has a dimension of time, right? So t over t times omega, t times 1 over t can give us a non-dimensional variable. But why did we define an omega instead of say characteristic time t naught, which possess a dimension of t, right? This is because by using omega, we can get a more meaningful and more elegant result at the end of the scaling process. Okay, so we choose to use the omega. We also have u. U has a dimension of what? L over time, right? So with L and omega, which has a dimension of L and 1 over t respectively, we can already get rid of the dimension of u, right? But here, again, for the elegancy of the final result, we'll introduce a characteristic velocity, which is called capital U. U we know, T we know, right? What's nebula? Nebula is this thing, right? And what about the xi? Xi has a dimension of what? Of length. So length is sufficient to take care of the dimensions of nebula. About the right-hand side, here, rho and nu are two special things. We can treat them already as a constant property, as a characteristic property of the system. Let's say we can just define rho to be the characteristic density of the system and nu to be the characteristic viscosity of the system, right? So we don't need to define them again. What about the pressure here? The pressure, maybe we could have defined a P naught to be the characteristic pressure of the system, but here we don't do that. We offer another way, which is rho u squared. I claim that by using rho u squared, I can neutralize the dimension of pressure. Let's check that. Rho has the dimension of what? Mass over volume, right? Mass over volume. And u has dimension of length over time. So this thing squared should give us m over lt squared. This is the dimension of rho u squared. What's the dimension of P? It's force over area, right? And force is ma. M times acceleration, which is acceleration L over T squared, right? M over LT squared, exactly the same thing. So later, by dividing the P by rho U squared, P over rho U squared, we can get the non-dimensional counterpart of P, right? So here, now we can say that we define rho U squared to be the characteristic pressure of the system. Okay, about the G. G here, we can also define a characteristic gravity of the system, right? The G is just the magnitude of the gravity acceleration vector itself. So we can say the G is just 9.81 meter per second squared, something like this. Okay, all the others we know how to do. So now we can define the non-dimensional variables. Xi star, all the non-dimensional variables, I will write a star next to it. Okay, xi star is just equal to xi over L, right? It's this, we can say it's the simplest way to get rid of the dimension of xi, because xi has the dimension of L. We divide that by the characteristic length of the system, we get a non-dimensional number. Xi star is this. And T star is what? T star, how can we get rid of the dimension of T? By multiplying omega, right? T times omega, because T has the dimension of time, omega 1 over time. U, very simple. U is just, let's say, Uj represents the velocity component on one direction, on the j direction. And this is just Uj itself divided by the characteristic velocity. Nebula. Nebula is what? Nebula is d over dxi, right? So xi, we know what it is. Xi is L times xi star. So we can substitute the xi by L times xi star. And the 1 over L is a constant. We can pull it out. What we are left with is this thing. But what is this thing? This thing is what we need, right? It's the non-dimensional nebula. Here, pressure. Non-dimensional pressure will just be P over rho U squared. The actual pressure divided by the characteristic pressure, right? G here. G vector divided by characteristic velocity. Okay, now we can transform the NS equation into its non-dimensional form just by using these relationships. Let's consider one term at a time, okay? First, du dt. Du dt. This thing is equal to what? Du dt is U is capital U times U star, right? So this thing is du star times capital U. And what about the t? T is 1 over omega times t star. This thing should be 1 over omega times t star. And here we pull out the constants. So what we get is u omega times du star dt star. Second thing, this thing is relatively simple because we just pull out twice the capital U, right? And then this thing will pull out 1 over L. So this thing will give us this. This 1 over rho is a constant. And here about the pressure gradient, let's pull out 1 over L and make this thing to be, make the nebula to be a star, to be a non-dimensional nebula. And the P, we know the P here is, well, where's that? Yeah, here. P equals P star times rho U squared, right? We can substitute this thing in. So the P here is just rho U squared times P star. And pull out the constant. Putting out the constant, we get that the rho is cancelled and U squared over L times the non-dimensional pressure gradient. G is just G star times G. Nothing special. Last one. Pull out twice 1 over L to make this thing a non-dimensional one. And the U, pull out once U, right? So here we get the non-dimensional Laplacian. Okay, now we can combine all the components of the equation and wait for harvest, right? U omega d U star dt star this plus U squared over L U nebula U equals to right hand side U over L this and G, and here nu U over L squared non-dimensional Laplacian. Okay, so we are one step away from our final goal. Let's simplify this thing, okay? We'll divide both sides by U squared. U squared. And then we multiply both sides by L. So what we'll end up with is this thing, L omega over U plus the coefficient here is neutralized. Same here, right? But here we have a constant which is called L over U squared times G over U squared. And here we have nu over UL Laplacian. Okay, so here is the elegancy of our final result. The equation here and here are cancelled, right? There are three coefficients left. These three are not random coefficients. They have physical meanings. Say this thing, L times the frequency, length times frequency over the velocity. This thing is called straw number. Straw number. It's a famous non-dimensional number in fluid mechanics. And here, GL over U squared. This thing is 1 over Froude number squared. Froude number is just U over square root GL. And here, this thing I think you are all very familiar with, right? What's the reciprocal of this thing? Velocity times length over viscosity. This thing is Reynolds, right? So the coefficient here is 1 over Reynolds. So this is why I think the final form we get, which is related to how we did the scaling process, right? Is a very elegant way, because our final result basically incorporates all effects that we can have in a fluid mechanics problem, right? When do we need a strong number? When omega, which is frequency, that is, if our problem involves vibration, let's say, right? So then strong number is useful. Here, when do we need Frost number? If we have G, right? If we need to incorporate the effect of gravity, then we need to consider the Frost number. The Reynolds number, needless to say, when we have nu, when we need to consider the effect of viscosity. So as I have said just now, our final result incorporates many of the effects, most of the effects possible, most effects present in a fluid mechanics problem. So it's a very comprehensive form. So now let's write out the final result. Strong number times this plus this equals pressure gradient times 1 over Frost squared G plus 1 over Reynolds Laplacian. So this is what we call the non-dimensional NS equations.